Hello students, in previous class we have studied the working of NMOS transistor. So today we are going to study the ideal volt ampere characteristic of NMOS or N channel enhancement MOSFET. We require this diagram to understand the characteristic. There are so many questions we can ask from characteristic. Why the current is varying linearly and why the current is not increasing even if by increasing the VDS. Therefore, we need this diagram. We have applied the DC biasing voltage. Already we have studied about this diagram. Now, by using symbol, we require some voltages, difference of these voltages across these three terminals. We need this diagram. Positive is applied to the drain and positive of gate is applied to the gate. Okay. And we have studied how this NMOS transistor is used as a VCCS. So, it is voltage controlled current source. Now, we have to understand the relation between ID current is flowing through drain terminal and it is coming out source and it is the gate terminal. So, what is the IG here? So, gate current in MOSFET is negligible, it is almost 0. Because of this, we have the greatest advantage in case of NMOS transistor, that its input impedance is very high. We will see in detail about these things when using the when we will be studying the biasing circuits of MOS transistor. What are the provisions to keep this condition intact? Now, here, so drain current is going into the device and coming out of the device through this channel. Okay. Now, let us draw the characteristic of this one. So, it is the ID versus VDS. VDS and ID. As it is fabricated on a silicon wafer, the currents are very small. The currents and voltages used in the device are in microamperes. So, it is 0 and we have the understanding up to this point the current changes or varies linearly. Whatever the voltage we change, VDS and gate voltage. So, this point is VDS saturation point, and how much it is we are going to write that also of this one. So, this region up to which the drain current changes according to the changes in gate voltage as well as drain voltage, and we have the equation for this, and this region is called as triode region or non-saturation region. Triode region. So, this current is ID max. We are going to write equation for ID max also, and this current up to this point it is not ID max. So, what is this current? So, let us write about the triode region first. So, it is the triode region on characteristic. It is also called as non-saturation region. Say this, and this current is given by equation ID is equal to Kn dash. So, it is W by L into VGS minus VTN into VDS minus, it is 1 by 2 or VDS by 2 square. So, this is the equation for current in the triode region or non-saturation region. So, this equation tells us that the drain current is some function of gate voltage as well as drain to source voltage. So, we can write clearly here. So, ID is function of VGS and VDS. But when this equation is valid, this equation is valid only for small values of VDS. So, we should write here ID or this equation is valid only for small values of drain voltage with respect to source or simply VDS. So, in this region the transistor is in non-saturation region, and see what is the other region on this characteristic. So, this region when drain current is 0, it means here VGS is less than VTN. So, it is the threshold voltage for NMOS device and the gate voltage is still less than the threshold voltage. So, what is the current? The current in the device is leakage current and it is very small amount of current, less than nanoamperes. So, almost there is no current and device is said to be in cutoff state. So, this region is called as cutoff region. Device is in off condition and here device is in on condition, but it is responsive or it gives response to the changes in gate voltage and drain voltage. The drain current depends upon both voltages. When this transistor NMOS is used as a switch, it is operated in non-saturation region and the cutoff region. So, it is the off state and it is the on state of the device. And when the transistor is used as an amplifier, the most useful region for this is saturation region. Okay. It is quite opposite to the BJT. In bipolar junction transistor, it is active region, but here in case of MOSFET, the saturation region is most useful when the device is used as an amplifier. We will see how it is useful. Now, see what is the drain voltage during this period. In triode region, what should be the drain voltage so that this drain current will change according to VGS and VDS. So, the condition for this is VDS should be less than VGS minus VTN. This VGS minus VTN, so this voltage is called as overdrive voltage. So, it is VOV is nothing but VGS minus VTN. See this. So, drain voltage is less than, VOV, overdrive voltage, and at that time this device works in non-saturation region. And what is the voltage between drain and gate terminal? There is no power supply, but we can measure the voltage difference between the 2 points. This voltage is also very important. It plays an important role in the device characteristic. See this voltage is, this is VGD, the voltage between gate and drain terminal. So, this voltage also be maintained if you want to keep this transistor in non-saturation region. So, this voltage must be less than, so it is VGD must be less than VTN. This should be VGD must be greater than or equal to VTN. When we maintain this voltage above this, at that time this device is in non-saturation region. If this condition changes, the device goes into saturation region. We will write equation for that also. So, this is all about the triode region or non-saturation region. What is saturation region? Where the saturation region start? The saturation region start at this point. So, at this point it is the maximum current, ID max, but when the device is driven into saturation, that is important one. See what happens, this gate to drain voltage. So, this voltage goes below VTN when VGD is less than, it is VGS minus VDS is less than VTN, the device goes into saturation. See this. So, difference of these two voltages VDS and VGS, the difference is less than is VTN, at that time the device goes into saturation. Or we can also say when VDS is greater than VGS minus VTN. So, here this is the condition, VDS saturation is nothing but it is this voltage is greater than VDS saturation is greater than VGS minus VTN. At this condition, the device goes into saturation. The device goes into saturation means what happens? Okay. So, here I will say the current remains constant from this point. The current remains constant at one value. We are increasing the VDS here. See this, the voltage on drain is increasing, but the current is not increasing. The question is, why current is not increasing? Let us see here. See this point, it is VGS and VDS. The voltage difference between these two terminals. So, this voltage is VGD and this voltage comes below the threshold voltage VTN. So, because of this what happens, the channel gets pinch off the drain end. So, here the channel is pinched off. If you see this diagram, so this portion the channel gets pinched off. One will say the channel is pinched off, here there is no channel, the current should be 0. How come it is constant? But it won't be 0. Why? Because you see this region is completely substrate region. This is substrate and here we have depletion regions. See, depletion region around this, and here also there is a depletion region. This area is having depletion region. The electric field across this is same. What is the potential difference? It is VGS minus VTN, it remains constant. The voltage difference here is constant and here electrons penetrate the depletion region and they reach the drain. Drain is at higher potential and VDS is increased. In triode region, VDS is small, but here VDS has increased, it is more than 0.2 volt. Because of this, electrons get penetrated in the depletion region and they reach drain. and the rate of reaching the electron is constant through this pinched off channel, and the drain current almost remains constant, and it is said that the device is in saturation. Okay. Saturation means at constant current is flowing through the device. In that constant, saturation word is used. What is the saturation current? The drain current when the device is in saturation is given by, it is half Kn W by L, half Kn dash W by L, it is Vgs minus Vtn square. See this, this is the non-linearity between drain current and the gate voltage. So, drain current, this equation is non-linear, non-linear relation between ID and VGS, because it is the square law relation. ID is proportional to the square of the VGS minus VTN. So, because of this, it is this square law relation between ID and VGS and VTN. VTN is the constant voltage, it is threshold voltage, it is constant for particular device. Here the variable quantity is gate voltage. Now, see, the most interesting part here is why MOS transistor is useful in saturation. Okay. If you see bipolar junction transistor, this region is called active region. Okay. The input current changes and the collector current changes, but it is the active state of the device. But here it is not the input voltage going into the device, only the gate voltage is changing and the drain current correspondingly changing. We want this kind of relation in the device, and here we can obtain that relation. So, here this region, if you change VGS here in this equation, you will get one more characteristic. See this. So, this one is, suppose this is VGS maximum, suppose VGS 4, it is the maximum gate voltage applied, it can be VGS 3, and VGS 4 is greater than VGS 3. Now, see, this region is saturated for this one gate voltage, but it is the desirable feature of the device, it is made to do like this, to behave like this. So, it is VGS 3. If I change the gate voltage, one more gate voltage, I can get this another curve, it is say VGS 2. Now, see, the device is the drain current is changing according to the square law equation here, and because of this, when this transistor is used as an amplifier, it must be operated in the saturation region, because we want a swing in the output current according to the swing in the input voltage. So, all the voltages and current we have written here are DC conditions. Okay, all DC voltage, VDS is DC, ID is DC, VGS 3, VGS 4, VGS 2, all are DC voltages. When it will be designed, amplifier circuit will be designed, at that time input swings will be there, AC is applied, and we want the device should respond to the swing at the gate, that is the AC changes should produce corresponding change in the output current. So, this is the saturation region of the transistor. So, it has three parts: triode region or non-saturation region and cutoff region. In cutoff region, the drain current is almost 0, it is the off state of the device, and third one is saturation region. The current in the saturation region is given by this. We can write this as, in terms of overdrive voltage, we can write this equation as ID is equal to half Kn dash, it is W by L. So, it is the square of overdrive voltage.